morning, everybody. Welcome to our seminar. Today, our guest is Fellous Asiani from Warsaw University, and the title of his talk is more or less about magic states and some resources which are going to be optimized. Marco, the floor is yours.
So hello everyone. So yeah, I will present to you this work about magic states, which is on archive now. So magic states are really the most important resource to optimize. So the outlook of the presentation is that actually a big portion of the presentation will not strictly be about the paper, but to give some element to understand the quick introduction to quantum error correction and then fault-tolerant quantum computing. And then I will present the result of the paper in the second part. Okay, so let's give some basics, because of course those basics will be useful to understand the paper. So let's talk about classical error correction. So imagine that you want to send a bit through a noisy communication channel, and you have a probability P that this bit is flipped. So right now it's classical. So in that case, if your receiver receives the bit 0, basically it cannot know that if the bit sent was 0 and no flip occurred, or if the guy wanted to send you the bit 1 and a flip occurred and you receive 0. So it's impossible to know, and you will be wrong with a probability of order P in your estimation. So a way to avoid this is simply to repeat the message. So then you ask the sender not to send the bit X, but the bit string XXX. So you encode your logical bit into 3 physical bits. And then as the receiver, let's say you receive the bit string 010. So then you guess that it's more likely that the middle bit has been flipped, and actually he sent you the bit string 000, meaning that he wanted to encode the information 0. And basically, by doing this kind of majority vote, you are now able to resist against 1 bit flip. But you can still be wrong in your estimates, because it could also happen that actually he sent you the bit string 111, and the 2 bit at the edge flips. But the thing is that it's less likely. This is something that will come with the probability of order p squared. So basically, if you do this kind of repetition strategy, your probability of error, if you did not encode, will be of order p, and if you encode, of order p squared, because you can resist against a single flip now, and you are stuck with 2 flips. So you improve the reliability of the transmission. So in quantum error correction, you would like to do the same, but the problem is that in this example, while you know which error occurred, you also know which logical information was stored. Because when you do this majority vote, here, basically, you know that the middle bit has been flipped, but at the same time, you know the information that was stored. And this is a problem for quantum error correction, because if we want to resist against error in the middle of the algorithm, we are not supposed to know which logical state is encoded, because otherwise it will collapse the information. So that's why we cannot do a direct analog. So the key thing in quantum error correction is to know which error occurs without knowing which logical state is encoded. So it's a bit tricky. But it's possible. And here we start with pedagogic example before going to more general cases. So imagine now that you want to send a logical qubit, A0 plus B1, with this noisy communication channel. And with some probability P, this qubit can be flipped. So if you directly send this qubit, it's a problem, because then with the probability of order P, you're wrong in the receiver is wrong. So, and yeah, and I assume a bit flip channel. So it's a specific noise model so far. So what I can do is then to encode this logical qubit in this state. So you see, it's not a copy of the 3 logical qubits, it's an entangled state. It's not a tensor product style. And what the receiver can do is basically that the total Hilbert space spanned by the 3 qubits can be cut in 4 portions that are defined by eigenspace of observable that commutes, so poly-observable. So for instance, there is this space here that is spanned by 0, 0, 0, 1, 1, 1. And here, those 2 poly operators, Z1, Z2, and Z2, Z3, their expectation value give +1. Then you have this space here, where the middle qubit is different from the 2 other. Sorry, I will take this one, it's better. So the last qubit is different from the 2 other. And here, if you have your poly measurement, the last qubit, the Z2, Z3 will give you -1, and Z1, Z2 will give you +1. So basically, this poly string, they detect parity between your qubits. And what happens is that, let's imagine you have this state and you had no error. So if you have no error and you measure this polystring, you see that the parity between the two first qubits is the same, and the parity between the two last qubits is the same. What I mean by parity is that they have the same value in the full expression here. So then if you measure this observable, they will return you +1, both of them. But if you have one qubit that has been flipped, for instance, let's say this here, the last qubit that has been flipped, when you will measure this poly operator, you will detect that you have a problem in parity of the two last qubits, because Z2, Z3 will return you -1. But the two first qubits have no problem in parity, because Z1, Z2 will return you +1. And basically, by doing this, you're then able to identify which qubit has been flipped. No flip, you will be in this subspace. And if you have a flip, depending on which qubit has the flip, you will be in this other subspace. And then you can deduce which error occurred, or more precisely, which qubit has been flipped. And let's say you're in this space, then you know that it's the last qubit that has been flipped, so you can flip it back and fix the state. But like in the classical case, it does not always work, because what could also have happened is that you start with this state, and actually the two first qubits flipped. And here you will end up in the same subspace, because the two first qubits have the same parity, and the last one has a different one. And then if you flip back the third qubit, because you will think that it was the third qubit that flipped, because your code is able to resist against one error, you will basically do a wrong correction, because you will flip back the last qubit and it will give you a logical error. So that's essentially the idea. You can resist against one error, but not two errors, like in the classical case, but then two errors are less likely, so you improve the fidelity overall. Yeah, so without quantum error correction, the fidelity will be 1 minus something of order p, and if you do error correction, it will be 1 minus something of order p squared. So now you can also resist against arbitrary errors, a single qubit error. So I will explain what I mean by that. So imagine you have more powerful code, essentially, but they are based on the same principle. And let's imagine you have 5 physical qubits, I'm coding one logical qubit here. And imagine that only one of the qubits is affected by an arbitrary CPTP. Then you have a theorem that is called the error discretization theorem that tells you that if you have an error correcting code able to resist against, if this n was either a bit flip or a phase flip channel, then you can correct for an arbitrary CPTP channel. So you have code that can do this. And what it means is that this noise map here, I can completely remove it, effectively inverse the noise if you want, and restore completely the information. So that's what we mean by single qubit error in this marginal context. When you have arbitrary CPTP map, it's a CPTP that will only affect one of the qubit of the encoding. Now you might say, okay, but in practice, I would never have this. In practice, it's more realistic that all my qubits are affected by a noise map. So I agree with you. But the thing is that it's the same idea. It will not be able to resist against all error, but it will be able to correct the most likely ones. So it corrects error at leading order. So here I will take a specific noise model just to give you the intuition, but it really works for arbitrary CPTP. As long as the noise is not too strong, it improves the fidelity. Imagine that this noise map is a mixture of 1 minus, so P is a probability. So with 1 minus P, you do nothing. And with the probability P, you apply some CPTP. Then you can expand this with time of order 1, no error occurred, time of order P, only a single qubit were affected by an error, a time of order P squared, 2 qubits were affected by an error. Error correction will be able to remove all the noise here, and here it will be static. But then it's the same idea. You remove leading order time in the noise. So if noise is sufficiently weak, you improve the fidelity. And when you have arbitrary, when you have this more powerful codes, basically, it's exactly the same idea as I said in the qubit codes. You're totally bare space, so you can have many different encoding, but it will be split into different subspace that will be defined as the common eigenspace of some poly operators. If all those poly operators return the eigenvalue +1, no error. And if some of them return you some -1, you know that an error occurred, you can identify it and correct it. And again, if you have too many errors, you will make a wrong identification, so you will introduce an error. But at leading order, you improve the quality. And so in terms of terminology that I will use after, what I call the syndrome is the result of the measurement outcomes. Okay, so now let me explain what is fault-tolerant quantum computing. Yes.
I suppose this measurement can will definitely disturb the state, right? It collapse state to.
Okay, good question. I did not comment enough. I will go back to the. I will go back to the qubit code so that you understand. So here, imagine you measure this observable, Z1, Z2, Z2, Z3. You see that you detect the parity, but you do not have access to A and B. It's a measurement that is not destructive on the logical information that is stored. So indeed, it could perturb the state in general. If you have some error that, here I took simple bit flip, but you could imagine also a complicated rotation so that it's not, the error will not bring you necessarily to orthogonal subspace. You can have a superposition, you can get the superposition between the subspace. Yeah. But the key thing is that the measurements you do, maybe they will collapse the state, but never reveal information on A and B. So it's not destructive on the information that is stored. Okay, so now let me talk about fault-tolerant quantum computing. So fault-tolerant quantum computing is a different, I would say, complementary theory to quantum error correction. So it tells you things that error correction does not tell you. For instance, how to correct error when the correction itself is noisy. Those measurements, they can also be noisy. So all what I explained before, it was in the noiseless case. How to implement an actual computation and not just a memory. Because we also want to manipulate the logical state. We don't want just to do a memory, like I explained before. And how to reach an arbitrary level of accuracy. Because I said, okay, if you have a single error, you can resist against it. But what if you have two errors? What if you have three errors? You would like to make your computation more and more reliable. So that's the complementary theory to quantum error correction that tells you how to do this. So the way a quantum computation, fault-tolerant quantum computation is done is basically like this. I will explain why after. I just explained how it is. So basically, you encode your logical qubit are encoded with physical qubits, and you initialize the logical state. Then you do error correction, a round of error correction, what I said before. You do a logical gate, error correction, logical gate, and so on until you measure at the end. So you see that each logical gate is sandwiched by rounds of error correction. And again, you should see each of these boxes. Here they are the logical level, but they are encoded in practice with physical gates acting on the physical qubits, and each of these gates can be noisy. So yeah, implementing the computation this way will guarantee that the computation is reliable, even if every component, including the correction of error, is noisy. I will explain why in 2 slides. But for this, I need some definition so that you understand. So we have 2 concepts here. We have the notion of faults and the notion of errors. So here I will assume a polynoise to simplify just for my explanation. So basically there is some probability to introduce an error after each gate for each of the physical gates, so that encodes the logical ones. And so a fault will be a gate that did not operate properly. So a gate that introduced error on the qubit. So a fault is the property of the gate and error a property of the qubit. So here we have this fault, and then it was a 2-qubit gate, so it might introduce error on the 2-qubit it manipulated. And then this error, after that, imagine that all the other gates are noiseless, are perfect. Even though they are noiseless, because we have a 3-body interaction, this error will propagate to more qubits. And then they will propagate again because of this other gate, and then again. So here we have a single failure in the circuit that can introduce error that damage 4 qubits, just because of the way error propagates. And so again, crucial point, a fault is the gate that did not operate properly, and an error is the impact on the qubit, and this error can propagate throughout the circuit, but fault is static. The last thing I need to define, so you understand, is the notion of extended rectangle, also called XREC. So this is a set of physical gates associated to the components that are shown here. So for instance, here we have the state preparation followed by error correction. We call it, this is the set of physical gates that will be inside this, because I recall that all these stuff are encoded. all the set of physical gates inside. This is what I call the extract of a state preparation. The extract of a logical gate, it will be the logical gate sandwiched by two error correction protocol, and the extract of a measurement will be the measurement preceded by a round of error correction. And you see that then those extract overlap. For instance, the extract of the state preparation, it overlaps with the extract of the next logical gate. So now we are ready to understand how we can make computation ideal, even if every component is noisy, under some assumption, of course. So I represent again here, so we have the encoded logical qubits. And here, I will make first an assumption about the noise. I want it to be not too strong. So basically, it's an assumption on the fault. So I will assume a non-correlated noise model. This is common in this field. And I will assume that the faults are sufficiently sparse in the circuits in the sense that there is only one fault per extract. I do not allow to have two faults. So how is it possible physically? If the probability to have a fault is sufficiently weak, then if you want, the fault will not be too condensed. They will be relatively spread in time. So it can be guaranteed if the probability of fault is sufficiently low. And then I will make some assumption on the way each of those elements are implemented. So I will explain the assumption while I explain the general principle. So I will make assumption on state preparation, error correction, logical gate. Okay, so let's start here. So here I have put, you see this red cross, there are faults that I have put under the condition that I have only one fault per extract. So here I have a fault on this state preparation, but then I cannot put a fault on this error correction gadget because it's in this extract. Here I have a fault in this logical gate, then I cannot put another fault, for instance, here. Just have one fault per extract. So let's start with the state preparation. It has to satisfy some axioms. So the axiom is that a state preparation is said to be fault tolerant if when there is one fault inside the physical circuit that does this state preparation, the logical state that is prepared has less than one error. So here I have a fault, so I might have an error, but one error on my qubit encoded the logical one. And then this qubit here, it's not faulty because I cannot have two faults per extract. And so then I look at the axiom of error correction, and it tells me that if I have no fault in the error correction box, but my input has at most one error, error correction removes this error. So it removes the error after. And then I have a logical gate. This logical gate has a fault, but its input has no error. So I look at the axiom of logical gate. If I have less than at most one fault, but the input has no error, the output will have at most one error. So I will assume it has one error. It's here, and then there is another QAC with no fault, so it can remove the error. Then I have a logical gate that is non-faulty, so it will not introduce error. Then here, for instance, I have an error correction that has a fault. So error correction is doing something wrong here. So then I look at this axiom. It has one fault, but its input had no error. So then the output will have at most one error. So we will have one error here. Then you have the logical gate. From the axiom of the logical gate, this error will be preserved, but then you have an error correction that will remove this error. And we get to the final step. So let's assume the final measurement had a fault. I look at the axioms. If a measurement has less than one fault, but its input had no error, it's resilient if you want to this fault, it can still recover the noiseless implementation. So here you see that as long as I craft my circuit properly to implement each of these operations, I have to satisfy some axiom. And as long as my faults are sufficiently sparse in the circuits, I can guarantee a reliable computation, even if everything is noisy. State preparation, error correction, a measurement, and so on. So that's the basics of fault-tolerant computing. So this assumption, here you have to trust me that you can make circuit like this. This is actually not trivial, but it will really impose constraint on how the circuits are crafted. I will give example later. And in terms of terminology, a physical implementation of a state preparation, error correction, a gate or a measurement that satisfies this axiom is said to be fault tolerant because it's compatible with this theory. Okay, so now I will finish this general introduction before going to the paper about concatenated code and the quantum threshold theory. So, how do we define the logical error rate of a fault-tolerant gate and how to increase the accuracy to an arbitrary level of accuracy? We could have 2, 3, 4 errors, so how do we do this? So here, as I explained, if you have one fault per extract, it's fine. The computation is reliable. So then it means that we might start having a problem if we have two faults per extract. And this comes with a probability that is 2 among A, where A is the number of fault locations, so it means the number, roughly the number of gates inside the extract, P squared, because it's two errors, so it's an uncorrelated noise model. And then this is the probability that an extract fails in the sense that if this occurs, I cannot guarantee anymore that my computation will be reliable. And basically, you can define the probability of error of a logical gate in the sense that a logical gate, you should see it as an extract in some sense, because this is the thing where I can understand, where I have too many faults, it breaks the success of the computation. So basically, all these extracts, you should see them as a protected state preparation, a protected logical gate, a protected measurement. And here, this PL, 2 among A P squared, is the probability that one of such components fail. So you should see it really as a probability of error of a gate or state preparation at the logical level. So now, okay, we could reduce P from this value, where we might not be able to resist against the noise, this probability of error of a logical gate, that is P squared. But okay, it's not a big reduction. How to do more? So here there is a cooking recipe that is called concatenation. So basically, you look again at the circuit and you expand it on the physical level. And what you will do now is each physical qubit you see and each physical gate you see, you will replace it by a logical qubit and a logical gate followed by a quantum error operation. At the end, if you do this for every gate, every logical gate will be sandwiched by error operation, because for instance, here you add error operation after, here also after, so every logical gate will be sandwiched by error operation. So why do we do this? Because then everything behaves as if what I called before the physical level, it's now a logical level, so it's more resilient. And basically, I just take the same formula here, but now I replace this probability of error of the physical level by a logical error probability. And here you see that I did, so when I do this replacement, now my logical error probability is P to the 4. And you can repeat it each time you have your physical level, you replace it by a logical level, K times. And at the end of the day, you have a formula like this, where the probability of error is P to the power 2 to the K. So what we call one concatenation is one such replacement. You have a physical level, you replace it by a logical, it's one concatenation. Then you look at the new physical level you have, you replace it again by a new logical, it's a second level of concatenation, and so on. And here we go to the quantum threshold theorem for concatenated code. So basically, if the probability of error is below, so I define P threshold, I define it like this, that's a definition. And then you can rewrite everything I said before like this. So if the probability of having, to be precise, a fault in the gates, it's not really an error, but a fault on my gate is below the threshold, which has this value. Then by increasing my K, the concatenation level, I can make as close to 0 as I want my probability of error of a logical gate. It has a cost because the circuit gets bigger. The circuit gets grow exponentially with the concatenation level, but the error decays double exponentially. So overall, it gives you a very favorable scaling. It's polylogarithmic in the good variable, let's say, for people familiar with it. But essentially, that's the quantum threshold theorem. Okay, so I'm almost done with this big introduction. So just to mention, concatenation is one of the very few approaches to fault tolerance, meaning to implement a complete circuit when everything can be noisy, including error correction. So it's one of the very few techniques to do this. There are other, like based on topology, that there are not so much. And there is recent work that also suggests that concatenated code, they could outperform, for instance, leading approach in the field, like the surface code. So there is recent work that has shown that this kind of, so you have to take very nicely chosen code to concatenate, but you can have a higher threshold than the surface code, and it can require less physical qubit per logical qubits for a typical problem, let's say. And so I think this is important to know because, I mean, in the field, everyone thinks in terms of surface code, but the situation is more, let's say, complex. It depends what you mean. Because here, the drawback you will have is that you will need long-range interaction for concatenated code, which is difficult to do experimentally. but it's possible actually it's possible in almost every platform apart superconducting qubits. Like you can do it in neutral atom, ion traps, spin qubits. But yes, so that's okay. Okay, so now we'll go to the paper in itself. Magic states are rarely the most important resource to optimize, so it's an archive. So what are magic states and why do we need them? So I will go back to this axiom for the logical gates, and I will not comment them again in detail, but let's assume that I implement my logical gate with this circuit. So here you see that if I have a single fault, as I explained before, it will introduce here 2 errors that may propagate into 5 errors. This is a problem, because this implementation of my gate does not satisfy the axiom of fault tolerance, because it should satisfy that if we have one fault and the input has no error, the output should have at most 1 error. But here a single fault created many errors, and then our correction will not be able to resist against this. So this is not a fault-tolerant implementation of the gate. To make a gate implementation fault-tolerant, what you can do is to make transversal gates. So a transversal gate, it's a gate that never couples different physical qubits inside the same logical qubits. So this is an example of a transversal gate. And why it satisfies the axiom I said before, imagine you have a fault in this gate here. It will only introduce 1 error. This error cannot propagate because you do not couple the qubits after. So, and you could check that this gate satisfies all the axiom of fault for the gates. You can also do interaction with transversal gates. You can make transversal 2-qubit gates. So you will create interaction between physical qubits. But the important point about transversality is to not couple physical qubits inside the same logical qubit. But if those are 2 different logical qubits, you can couple them. And to give an intuition why, imagine this gate had a fault. Then it might introduce indeed 2 errors, 1 here and 1 here. But per logical qubit, there is 1 error, because the 2 errors are spread on the 2 different qubits. And then if you do error operation on each of the logical qubits, they will see only 1 error, so they will be able to remove it. But the big problem is that there is a no-go theorem that tells us that it's not possible to do universal quantum computing with only transversal gates. There is at least one gate that will make the different physical qubits within the logical qubit interact, and then it will break fault tolerance. It means the axiom I said will not be satisfied, and all the reasoning I told you before will be wrong. So how can we make universal quantum computing if we cannot make universal set of transversal gates? It looks complicated because the error will propagate. So a way to do this is using magic states and using what we call magic state injection. So imagine I have a logical gate on a logical qubit here that cannot be made transversal. It goes in this no-go. It's not possible to make it transversal. So a way to implement it in a fault-tolerant manner is basically to use an ancilla logical qubit that is called a magic state. So it's a qubit prepared in some specific state that interacts with your logical qubit of the computation, and then you typically have a measurement, a feedback here. And basically this whole circuit will implement the logical gate you want to implement. But what is in their interest in the right is that all these gates here, they are transversal. So then they will satisfy the axiom of fault tolerance. I will have no problem to protect them with their operation. But some non-transversality must be hidden here, because otherwise I would just tell you the no-go is wrong. So the no-go is true. It's because to prepare this magic state, we need fundamentally to make the qubits interact inside. And if we are not careful, we'll have a lot of error that will be produced and will then propagate everywhere, and we are stuck with our operation. So fortunately, so basically what happened is that we moved the problem for making the gate fault-tolerant to a problem and making a state preparation fault-tolerant. And this is easier. Basically, we have protocol that can, when you prepare a state, an encoded state, they can detect if a single fault introduces many errors. You have a flag, and if the measurement tells you one fault introduced many errors, you do not inject the state. And you only inject it if you're guaranteed that so you don't know if the fault occurs, but basically your measurement will, if your measurement will say it's good, by construction of the circuit, it means that theoretically it's impossible that this circuit, a single fault, introduce many errors. So basically you can make this magic state preparation fault-tolerant and then compatible with everything that I explained before. But the problem is that, so first to make, so I will call magic gates, the gates that need magic state injection. Then you realize that first you need an additional ancillary qubit to make the gate. Okay, if it's just one qubit, it's not so big. But the circuits to preserve this state are quite complicated because it's fault-tolerant, so we need to be careful about errors that can occur everywhere, even in the detection, this flag detection, it can be faulty itself. So it's really a lot of tricks to implement, to be sure that the circuits satisfy the axiom, so they are quite big. And it's also based on post-selection, because basically, we cannot wait for the magic state to be ready because otherwise qubit will disappear. So we need to prepare a lot of them in parallel. And when one passes the test, we inject it. And so for all this consideration, their magic gates are expected to be very costly, and there is a significant part of the research that is about minimizing the cost of magic state preparation, reducing the number of magic gates in algorithm, etc. So that's really a big part of the research in, let's say, algorithm and quantum error correction. So in our paper, we analyze if magic gates are actually really much more costly than transversal gates for this concatenated code. So what is surprising is that there were actually no in-depth analysis on the question. So basically what people usually did is that they started from the assumption, okay, magic gates will be super costly. It's quite clear the circuit looks complicated. So let's optimize the way we prepare magic states and compare new ways to prepare magic states. But there are no in-depth analysis of the cost of magic gates compared to transversal gates. How much more does it cost? Like for some code, it's known that it can cost order of magnitude more. But here it's more like kind of rumors, if you want to say it simply. And so we analyzed this, and this analysis was possible because we developed an analytical approach to get close expression on the total qubit count to carry a computation. And so this is the thing that is quite general, like our approach is applicable for common concatenated scheme. And then there are more particular results, but that are true in a lot of typical examples, let's say. And basically that's because it's not possible to make a general claim here. You have to take typical implementation of how you will implement the code and look at what it costs. So we looked at various such typical examples, and we realized that if you entirely remove the magic states from a typical algorithm, when you have about 10% of gates that are magic, if you look at resource estimates, it will only reduce the total qubit count in the best case by a factor of 2 or 3, and usually by a few percent. But if you optimize the fault-tolerant implementation of error correction, the circuits that for a given code implements it, you can reduce the cost by orders of magnitude, so significantly more. And we give some example. So the conclusion is that optimizing the way you implement error correction should be the priority, not optimizing magic state. And this is surprising given the big activity in the field to minimize the cost of magic state and magic gates. Okay, so let me explain. So here I also need to define some things. So below you can see a general algorithm. So you have some transversal gate and some magic gates. So the cost of this algorithm in terms of qubits will correspond to the moment you need to use the most qubits, because they will define the cost of the algorithm. Because even if you use just one qubit before and 1,000 of qubits in the middle, you need 1,000 of qubits in your computer. So this bottleneck is defined by the moment you have the most magic gate in parallel. So why is that? The question is not if a magic gate will be more costly than a transversal. It's clear that it will be at least because you have one extra qubit. But the question is the cost just twice more or 10 or 1,000 times more? This is the question. And because again, you only have a few magic gates in algorithm, 10, 20%. So if it's twice more, it's basically negligible in the big picture. So basically, we reason with the resource estimate by looking at the bottleneck here, and essentially looking at the cost of this algorithm is the same as looking at the cost of this algorithm, which implement the bottleneck step at each step. And here it allows me to define what I call transversal qubits. So a transversal qubit is a qubit that will only see transversal gate in this equivalent algorithm, and a magic qubit is a qubit that will only see magic gate in the algorithm. So at this point, we did not replace the magic gate by state injection. This is done when we implement error correction. Okay, so let me first explain how we can estimate the resource of an algorithm that only contains transversal gates and transversal qubits. So as I said, when we have a transversal gate, if the gate we implement satisfies the axiom of fault tolerance, to go from the physical level to the logical level, we just implement the logical gate and we make it follow by our operation. And then it's fault tolerant because the gate and the operation procedure satisfy the axioms. And so here is the case for the transversal gate. They are naturally fault tolerant. So this is the replacement rule when I will go from the physical to the logical level. And to give an example, imagine here that this logical qubit is encoded with the 7-qubit code. So each orange line is a logical qubit. We will first have the transversal logical gate, and then we will have this error correction box here. And this error correction box is done by using logical ancilla. So they are not, they are encoded with physical qubits, but already at the logical level, you can see the error correction because you will couple this ancilla with logical CNOTs, do some measurement, and it will tell you which correction you should apply to remove the error. And basically, all the operation you see on the right, they are transversal, the logical operation. So it means that, for instance, if I look at what it looks on the physical level, each orange line is encoded. So it should be encoded with 7 qubits, but if I did this, the circuit would explode, so I assume it will be 3. And you see here that we have a logical CNOT, and it's implemented in a transversal manner. So this is the real implementation on the hardware, the circuit of the right. Okay, so now I did here a first level of error correction. I replace my gate in the algorithm by gate followed by error correction, which are encoded like this. Now I want to analyze the resource cost as a function of the level of protection. So I want to improve the level of concatenation. And to do this, basically, I look at the previous circuit at the physical level, and as I said, I transform everything into logical. As I said before, it's a rational construction. I look at my physical layer and I replace it by a logical. So here, then all the blue lines will become orange. They will become logical qubits. And all these physical gates will become logical gates. But here I will make some assumptions that are important to understand the rest. So to promote a physical level to a logical level, so there are two assumptions. The assumption 2 will mostly be for pedagogy, but the assumption 1 is key for the results. This is the assumption that will explain the result about matching, the main result of the behavior. Here we make the assumption that every physical gate inside a circuit composed of transversal gates is itself transversal. So so this is a key assumption that is the case in many codes actually. What it means is that, let's say you have, so actually I somehow already assume it in the last slides, but basically here, if I look at what this logical gate would look like, it will look something like this. It will look transversal. And I assume that then if I wanted again to replace this gate here, so here, okay, it's the same gate, it's a CNOT, so we know that it's transversal, but let's say, okay, for instance, these gates here, they are encoded in a transversal manner with these gates here. And I assume that if I did an extra level of concatenation, these gates, when they become logical, they will still be transversal. Basically, you will never need to have magic gates inside the transversal gate. That's the assumption. That's what the assumption means. Yeah. And the second assumption is that all transversal logical qubits will require the same number of physical qubits. So basically, it means that whatever qubit I look here, if I replace it by a logical qubit, it will have the same number of qubits. So this second assumption is often true, but it's mostly for a simple formula for my explanation. It's not very important for the result. So here again, it means that a physical qubit, when I promote it to a logical qubit, it's encoded with physical qubit, and it might need some ancilla to be prepared. But whichever qubit you look at, it has the same number of qubits inside when it's encoded. And so then, okay, the physical level become a logical level, and I apply the recipe I told you. So basically, each of these gates, now I know they are transversal by hypothesis. Inside transversal gate, I assume they are only transversal gates. And so then I use this replacement rule. It's transversal followed by error correction. So this gate in red here, it's a logical CNOT that is implemented in a transversal manner and actually followed by an error correction box that I did not represent to not blow up the circuit. But yeah. And okay, that's it. So you do this level of replacement. Then you have here, you expand your circuit in the physical level, and you do it again and again, k times. And when you have that, so under these two assumptions, sorry, so here there is a typo. This first assumption it's not only for pedagogy, it's the crucial assumption in the result, which again is true for interesting causes. So yes.
So when the physical qubits of within a logical qubit interacts with the ancilla physical qubits, is it not possible that they are talking to each other mediated by ancilla logical qubit?
So sorry, your question is if you have different physical qubits inside the logical qubit,
Yeah,
and some of them are ancilla.
yeah. So and ancilla the physical qubits are entangled.
It really depends. It's complicated to answer in general. It might depend on the scheme you look at, but they would be entangled at some point. Let's say.
Yeah.
Yes,
So
usually.
are the physical qubits within our logical qubit is not interacting
No.
through the ancilla?
Okay. So good question. So here, I think we need to go back to the axiom that we need. So indeed, we should avoid to make interaction between the physical qubit and coding a logical one. But it does not mean we can never do this, because what is important is those axioms. For instance, in the state preparation, it's okay to make the qubit interact. What matters is that if there is a single fault, I have no more than one error on the output state. So usually when you will make interaction, this cannot be satisfied. But then you can have post-selection procedure that when this occurs, you do not inject the state. So in practice, you will have interactions, but your protocol is such that if a fault introduces many errors, you just do not inject the state in the computation. You see what I mean? So this is really the important assumption. And in practice, it means you should not interact. But for state preparation, it's more subtle. You can interact as long as you have a flag that tells you, be careful. So yeah, in practice, this ancilla will interact with the. Okay, and so now, basically, when you analyze all this, another assumption I said, the total number of physical qubits is a very simple recursion, because at each level, you replace your qubit by a given constant, and then it's a self-recursive construction. So if you concatenate k times, you do k of this replacement, and each time you multiply the number of qubits by the number of qubits encoding a transversal qubit, so it gives you this simple. And again, the assumption I did, the second assumption is for pedagogy, it's not very important. The important assumption is the first one. Inside the transversal gate, at lower level, all the So if I told you, if you have transversal gates, the replacement rule follow like this. You do transversal followed by error correction. Because this gate follows the axiom of fault-tolerance. But if you have a magic gate, this gate does not follow the axiom of fault-tolerance. So what you do is you first replace it by a state injection gadget. And then when it's done, you replace each transversal gate by transversal followed by error correction. So this is fault-tolerant, no problem. And you replace this state preparation by a fault-tolerant magic state preparation that satisfies all the axiom I told you, which might require post-selection and so on. And here, this is the element that might contain magic physical gates. So basically, if you look at this qubit on the top here, all the qubits only see transversal gates. So inside the qubit encoding the magic qubits, the only magic qubit inside might be on this part of the circuit. Okay, and so now I do this assumption also to keep simple formula to have recursion in low dimension, you will see. So there is a single type of magic gate, only T gate, okay? And all logical magic qubits, they require the same number of either transversal or magic qubits, meaning that whichever magic qubit I look in my algorithm, when I look at encoding, it has the same number of transversal qubits and the same number of magic qubits inside as any other magic qubits. This is the simplest case you could have. And here is what happened. So when we increase the level of concatenation, each transversal qubit, I use the recursion I said before. it's replaced by lambda transversal qubit, again replaced by this, so it grows with lambda to the power k. But if we have a magic qubit, it is composed of some transversal qubit, the qubit on the top, and some magic qubit, the qubit on the bottom, here to create this state, because you have magic gates inside here. And so basically you have a tree construction, but whenever you reach transversal qubit, then they are only replaced by transversal qubit, because in a transversal circuit, there are only transversal circuit below. But if you have a magic qubit, then you have each time a tree like this. And then it gives you basically a 2D recursion formula, where at the beginning of the recursion, you put the number of transversal qubits you have in your algorithm and the number of magic qubits you have in your algorithm. Then you concatenate k time and you have a 2x2 matrix that will give you the number of physical transversal qubit and physical magic qubit, and the total number of physical qubit then is read like this. So here, so apart from the assumption that inside the transversal gate there are only transversal gates, the other assumptions are mainly so that you have a 2x2 recursion. Because you could imagine having many different transversal qubits, just that it will give a bigger matrix recursion. But at the end of the day, under this assumption that inside transversal there are only transversal, it will have a 0 on the bottom left, and that's the case again in typical codes that you have. Okay, so now I go back to the original question. I want to compare the cost of magic to transversal. So to do this, a good figure of merit is to consider an algorithm composed of QL logical qubit that only does magic gates, and another algorithm composed of only transversal gate that acts on the same number of logical qubits. And we compute the ratio of the number of qubits in the two circuits. So here, if this ratio is big, it means that this circuit on the top requires much more qubits than the circuit on the bottom. And when you solve this kind of equation, you basically have a simple formula like this, and you recognize the ratio of eigenvalue here. And you see that, yeah, so you have this ratio of eigenvalue. If lambda magic divided by lambda trust is less than 1, then the magic gate, they have a similar cost compared to transversal in the sense that they will only differ by a multiplicative constant. Meaning that when you increase the level of concatenation, the cost of magic gate will not explode. It will be asymptotically similar to transversal up to a global multiplicative factor. And so now I will argue that this is a typical case and then talk about the example. I'm almost done. So basically, so that's the key takeaway. And what does this mean physically? So this less than 1 means that there are less magic qubits encoding a magic qubit than transversal qubit encoding a transversal qubit. And this is actually typically we can typically expect this. So what I say is a conjecture, not a proof, but then it's verified with the example. When you have a transversal qubit, it only sees transversal gates. So this is a logical transversal qubit. And because inside transversal, there are only transversal gates, the physical qubits here, they will all be transversal. They will only see a transversal circuit. So here, all the qubit encoding a transversal qubit will be transversal. But if we look at magic, we do the replacement with the state injection protocol. And we see that, for instance, this top qubit here, it will only see transversal. And the only magic qubit inside, they might be on the bottom of the circuit. So that's the first guess to realize that actually, it could be that there are very few magic qubits to create a magic qubit. In some sense, to create magic states, you need only a few magic gates inside, loosely speaking. Now, this is not a proof because you have post-selection. So here you can have more states to prepare, so which can increase the number of magic qubits inside a magic qubit, but that's at least an intuition. And so then to check this intuition, we took various typical examples. So we'll not go into detail here, but we look at the 7-qubit code, a different way to implement the operation in a fault-tolerant manner. There are different gadgets to do this, different way to prepare the magic states, some other model. And in each case, we realize that typically the ratio is much smaller than 1, or it could be that it can be bigger than 1, but only slightly, so that for all practical purposes, magic and transversal gate will almost have the same scaling law in the. So now they will differ by a constant factor, and this constant factor could be big, but when you look at circuit, so it's big, but knowing the fact that you have typically 10 or 20% of magic gate in algorithm, at the end of the day, it doesn't matter too much. So then it depends on the case that you could reduce the cost of the algorithm by a factor of 2 or a few percent, depending on the case. But overall, it's not very costly. And so that's why we reached to the conclusion that for all practical purposes, basically magic state rarely costs enough to need optimization, because if you sweat a lot to optimize this, in the best case, you will have maybe a factor, you will divide your overhead by a factor of 2 or 3, but not by 1,000 or 100, like sometimes suggested. So I'm almost done. So that's the last slide. So if you're on scaling approach, so in general, as I said, you can have n-by-n recursion, even if you have a single magic gate. So in the paper, we explain how you can find a good dimension for the matrix, and how to find each coefficient, acknowledging all the details of fault-tolerance, post-selection, and so on. And basically, I'm not aware of any other analytical approach for concatenated code that gives such simple, because at the end of the day, the formula are pretty simple, right? It's just a matrix to some power. But acknowledging all the details of fault-tolerance with post-selection and I mean, with everything inside. And so I think that, yeah, usually it's more numerical plot. So I think it's nice. And okay, maybe just one quick comment. So basically, by optimizing circuits, you can reduce a bit this coefficient, which will reduce the cost of algorithm. But basically, we identify a trade-off between minimizing this thing and the threshold of your operation. If you want to optimize a lot your circuit, you might have a poorer threshold when you implement the circuit. Okay, so in conclusion, that's the last slide. So in this paper, we give a general scaling approach to find the qubits count in common concatenated scheme. So this is the thing that is quite general for concatenated scheme. So this approach can really give simple expression. And I don't know of like another paper that shows a very simple formula like this, while taking into account all the technical aspects. And then this is more specific, but arguably fairly representative of the general case, because you are forced to take example. So we took a code that is usually the one studied when you concatenate with many different ways to implement the operation, magic state, and in every case, we realize that if you optimize magic states, you will only gain a little bit. But if you optimize other aspects, like the way you implement your operation, you can reduce the cost by order of magnitude of your circuit. And so basically one message is that this should be the priority to optimize for this code, the way you implement your operation, rather than magic state, which had a big focus for this, also for this code. So yeah, thank you.
Thank you very much. Now it's time for questions or remarks.
Yeah. Okay, so thanks for the talk. My question is, instead of taking a magic state, if you take any other state, how good these magic states would be compared to those states? Is it possible to quantify that particular thing?
So you mean if you do not have a perfect magic state, but some okay, I think there are different ways to answer this. So
there is another thing I want to add with this question, that when we are thinking about this type of quantification, is this quantification is dependent on the task that you are considering? I mean, computational task that you are
for the cost of magic state. So I will maybe answer this first because it's easier. So here, the main assumption in our quantitative conclusion, sorry, okay, I will say it already. So the main assumption in our quantitative conclusion that magic is not very costly, we assume that the algorithm has no more than 10 or 15% of magic gates, but then there are no other assumption. And if you ask, and this is typical for algorithms, they will not have a lot of magic gates. So if you assume that, then it does not depend on the task. And so your other question was, what if you do not inject exactly the magic state you want, but another one? So do you mean there is noise, or you want to implement to prepare another state?
I want.
Okay, so then there is the question is, you need to find a way to prepare it in a fault-tolerant manner, because we can only prepare in a fault-tolerant manner very specific states.
Yes.
So if you tell me I don't want this state, but this state here, you need to find a circuit that can do this, and it's not trivial. So what you could do is to because if you have a universal set, you could of course prepare a given set and then apply gates and approximate your state. But then you will still, it means that in your computation, you will still use this basis for the preparation of state. So if you don't want to use this basis, but another one, it's a bit challenging in the sense that you have to find a circuit that satisfies the axiom of fault-tolerant preparation.
And there are some puzzles which are like known that you can do this for. Like I think there are like states implementing diagonal gates in the third level of the hierarchy. I think there are various instructions based on the hierarchy give you process states you can do this for fault-tolerant.
So maybe, yeah, an important moment is that the notion of magic state, what is a magic state? I think it's a bit community dependent in the sense that, for instance, for a magic state could be the plus state in the context of this, in the sense that it's a state that I use to implement a gate that is not fault-tolerant. Now, it often occurs in many codes that a fault-tolerant gate of the Clifford group, transversal gate on the Clifford group and not transversal or one element outside the Clifford, like the T8 or the Toffoli. So it's often the case, but it's not fundamental. You have counterexamples.
Yes.
Yeah.
Yeah, I mentioned that state listing. I had a question about the slide. I think you just flashed up right at the end about it looks like you mentioned a trade-off between like the lambda values and the thresholds you had.
Yes.
You said that your thresholds change a bit. Can you say how much? Yeah, a bit more about that.
So I can explain, intuitively why, and then I can. It's not very sensitive, but a little bit. So maybe just quickly to give intuition. Sorry, or is this was my slides? So here you do first selection on this state. If you have a finite number of magic states you prepare in parallel, you cannot guarantee they will all pass the test. There is a finite probability that you're forced to inject a state where the flag is red, told you should not inject the states. Many are propagated, but you have to do it. So the consequence of this is that it will not completely break the computation, but it will introduce more noise than predicted, and in particular, it will lower the threshold of error correction. And so then you can have, basically there is a trade-off in the sense that the more magic you prepare in parallel, the bigger the coefficient in your matrix are, because for one magic gate, there will have more qubits inside. So the lambda will be bigger, but it's less likely you inject a wrong state, meaning that you do not touch the threshold a lot. But if you reduce this, it's more likely you inject a bad state, which modify the theory, let's say, of error correction and make a poorer threshold. Because the threshold in the theory was implicitly derived, at least for this code, under the assumption of an infinite resource. Because they assume I always have a state that passes the test.
Yeah.
At least finite resource is not possible.
Is it possible to do like analysis of what happens if I just like keep trying to produce magic states until I get one that works? Like, can you do like on average over this probability? This probability or something?
So that's a good question. On average, so that's also something that is surprising because people say it's very costly because you have post selection here. But the funny thing is that, so okay, on average, it depends on the circuit. But let's say because we look at different implementation, but let's say the order of magnitude is that you will need 2 magic states per place. But the thing is that it's concatenated. So it's a 2 to the power k.
Yes.
Yeah, because at each level. But the funny thing is that people say, oh, magic states are very costly because this costs a lot to prepare. But you also need, at the very beginning of your computation, you also need to fault-tolerant initialize your state. And the number of extra states you need for the magic or for just to prepare a 0 state is not very different. It's a bit higher for magic state, but the difference is not so big. So this is why, it's not specific, at least in this code, I'm not talking about other codes, for the concatenated code, it's not specific to magic state, this problem, post selection.
Okay, yeah, that makes sense.
In this earlier matters, the non-transversality was introduced by magic states, and when you concatenate, you use concatenated protocols. How is that circumvented?
Sorry, can you repeat that?
How is Noble theorem circumvented in your approach?
So by doing magic state injection. So for instance, this magic gate is not transversal, but then to implement it, I implement it with this circuit on the right here, because all these gates are transversal. There is still the problem of this no-go, which is hidden in the fact that this magic state, it needs interaction inside. So it's not transversal, this preparation. But it's less a problem because we have protocol based on post-selection to guarantee that by post-selecting the good state, one fault cannot introduce more than one error. So it's circumvented by doing a state injection gadget and crafting specific protocol to prepare the magic state. We move the problem to a problem of preparing the state, if you want. And this is easier, let's say.
Maybe I have one
Yeah.
elementary and academic question. It's all about qubits.
Yes.
Does this formalism apply to higher dimensional systems?
So the thing is that, so a naive answer will be yes. For me, I don't see what will fundamentally, I don't see a fundamental reason why it will not work. Let's say the problem will rather be that to develop fault tolerance for higher dimensional systems, like you have for continuous variable, this kind of thing. But for instance, if you have two treats to check all the axiom of fault tolerance with more than one level, maybe some people did some work, but so I would just say I don't see a fundamental reason why
In
no.
principle, it's not impossible.
No, I don't see
Okay.
this.